Now we're going to talk about a little bit more of the quality of the information going past. So we're going to talk about QBR and how to improve the streaming efficiency and the quality. And we have Kumar Subramanian. Did I say that right?
Yeah, that's right.
Okay, thank you.
Hi. Good afternoon, everyone. Great to present at SMPTE. Thanks for your interest in what MediaMelon does. Just a quick background to MediaMelon. It's a company based in San Francisco, and our vision is to improve streaming, not encoding, not players, not CDNs. So we don't look at improving encoders or coming up with new codecs, but we want to. Our aim is to improve streaming independent of various encoders, which is QBR. Besides QBR, we also have solutions that capture streaming performance. We have a streaming analytics platform and a technology to route videos through the right path so that quality can be increased and it is streamed in a more cost-efficient manner. But this presentation is going to be about QBR. And what I'd like to do is to structure this presentation in 3 parts. The first one is about what would be the ideal way. What is it that we desire? What is missing in current methods of streaming, and what would be good to have? Second, I will explain as to how QBR works in a couple of block-level architectural diagrams. And the third part, where I'll spend more time, would be to share some results of a recent study that we did with Informa TV. So QBR, so let me first start with, what is it that we hope to achieve? So an encoder typically would take a video and encode it into multiple bit rates, multiple representations. So in this example, let's say there are three representations. You can, it's the same principle whether it's VOD or live. You can do end pass, but at the end of the day, you are creating a few representations. And you have a manifest file that describes what those representations are, and it goes to a player, whether it's Dash or HLS or whatever. The player looks at what are the various options available and picks a representation that is less than the bandwidth available, typically. I mean, different players have different strategies. You might want to start slow. You might want to wait for a few segments to download before you start playing. But the general principle is that the player would pick the highest bit rate given the bandwidth that the player is able to compute. So the first example on the right side would show what a typical ABR, how a typical ABR mechanism works. So it might start with a lower bit rate just to get things started at quickly, and then move to a representation that is below the bandwidth. As the previous presentation described, normally bit rate and quality are correlated. Normally they go together, but the extent to which bit rate and quality are related depends upon the scene. It changes on a frame-to-frame or a segment-by-segment basis. So ideally, what you would want to see is that in scenes where the quality is the scene is not very complicated, you might want to pick a lower bit rate, and by doing that, you want to save on the bandwidth. And what you would also want to see is that when there are scenes that are very complicated and that can benefit from a high bit rate, you would want to ideally be able to go beyond the bandwidth and be able to download that. Now you might think that you could do it with a VBR, the second at least, but the problem is that you could encode a video in VBR, you could have scenes that are complicated, be at a very high bit rate, but it won't stream easily. Because the way that a player would, you could do cap VBR, and then the question becomes what the cap is, and then how much you can have a variation from a given advertised representation. But with this, but what would be ideal is if you can stream a CBR encoded content as though it's VBR, or conversely, if you have a VBR encoded content, be able to stream it actually, because there are challenges in streaming it. So that's what we would one would like to see, and I'll describe as to how QBR works. And at the end of the discussion, what I would also like to propose to this group is how we can invite ideas onto how we could collaborate with player companies and encoder vendors and CDNs, because this principle essentially can help various parties. So the way QBR works is that it describes the quality, as the previous presentation indicated. There are various ways to quantify subjective quality. We have a way of doing it, but there could be other ways. We have a referenceless method to compute visual quality in a near real-time basis. It can be fully real-time, but if it's, at worst, it can be, it's done with a few, with a 150 millisecond delay. It computes the quality at every frame and hence every segment, and then it figures out what is the video structure, in the sense how much quality varies with every segment, how closely packed the complex scenes are, and creates a small metadata file that describes the whole video. For a VOD file, it's simple. You can have one metadata file that you can compute, that you can create after encoding, before encryption, and that metadata file provides kind of a hint map on the whole video. If it's a live, it's created along as the video is comes out of the encoder. And the metadata file is then used by the system in two different modes. I'll describe one that doesn't require anything on the player, and the second one is assisted by an SDK on the player side. The first one essentially would take the metadata file, the information on a segment-by-segment basis, and it changes it replaces frames or GOPs such that a lower representation can be used in the place of a higher representation at scenes which are not complicated enough. So that at the end of the day, you can get the same quality for 30–40% lesser amount of bandwidth, as some of the results later on will show. And this method works across various encoders. It's encoder independent, and it also comes with a dashboard where you can really see how much quality is improved and how much bandwidth is saved on a near real-time basis. The second method actually provides the full benefit of QBR. And to do this, we take assistance from an SDK on the player side, and we are working with some selected number of players today. So here, the metadata file is computed, and then it is sent to a player that can understand that metadata. What's essentially happening is that the player's adaptation engine performs as usual, but it is guided by visibility on what is there in the video at every segment. So a player would look at the bandwidth and the available bit rates and pick a given bit rate. And in that situation, it would query the SDK, which has information on what is in the video, and that SDK would inform the player to pick a lower or a higher bit rate. And by doing that, you are getting advantage of sometimes improved quality and sometimes reduced bandwidth. So a given file can be streamed with an advantage of improved performance as well as higher bandwidth efficiency. So that's basically a quick description on of the way that QBR is implemented, the two methods, one with player assistance and the previous one without player assistance. So another way to think about it is with ABR, the player is at every segment, it receives a choice of bit rates, and it picks one, and that's about it. The player, however smart it may be, will not know what is in the video, typically. With QBR, we think of it as having a GPS, so that you can see what's coming ahead and can make better decisions. So in certain scenes, it may pick a lower one and build some buffer with the view of what's coming ahead, where it might need to pick in a higher bit rate so that the quality is improved. So we did some tests along with our partners at InformiTV, which I'll describe in detail. So let me just go to one slide forward and come back here. So the test involved a race car sequence. One might typically think that it might work if the video is not very complicated. There's a lot of scenes where you could get by with a lower bitrate. So we purposefully took a video that was a race car sequence, a NASCAR video. It had extremely complicated scenes. The camera panning through the audience, through the cars, and then going back and forth. And we encoded at a 2-second segment basis with 6 bit rates. We used a standard DASH reference player. We tested the playback multiple times, 5 times in this case, and we computed what happened. So here is a visual of this. And if any of you wants to try it for yourselves, you can contact Media Melon, and we can provide a link to this player to you. So this image shows the video player. It has superimposed on it a graph that would show what the ABR selection would have been at every instance, and what the QBR assisted ABR selection would be at that same instance. So the orange line is the ABR selection, the blue line is the QBR selection. So you would sometimes see that the QBR selection is lower than the ABR one, and sometimes it's higher. So in this case, we have watermarked the video with the bitrate so that you can visually see how the bitrate changes with every segment. You also have statistics that show what the cumulative benefits are. So from the time the video was started, how much bandwidth was saved, as well as it shows how much the quality was improved. So we can show this in terms of a MOS score, the referenceless MOS score that we described earlier. And it also shows the percentage of segments which were uplifted, basically getting a higher MOS score, and how much the bandwidth savings were up to that point. So based on the 5 different runs that was done by our partners, let me show you what the results were. So with ABR, the bandwidth, because of bandwidth variations, the bitrate selection at every segment was in this form. This is just a representation of the principle of ABR. So you have an average, a mean ABR through the course of the video, and it shows what the segment selection was at every point in time. With QBR, there are 2 modes actually. One of them prefers, gives a higher emphasis to quality improvement, and the second one gives a higher emphasis to bandwidth savings. But in both modes, both quality improvement and bandwidth savings would happen. The settings would influence the weightage for one over the other. So in the quality mode, you would see that the chances that the blue line is over the yellow line is much higher. The way we look at how these modes would influence adaptation decisions is we really in the bitrate savings mode we would not want the bandwidth to go below a certain MOS score, but save as much as we can. Whereas in the quality mode, we would try to get as much content downloaded at a lower bit rate in scenes that don't matter to, with a view on pulling the segments at a higher bit rate during the scenes that can benefit from a higher bit rate. So with these 2 modes, what we saw was with the purely quality savings mode, we were able to get a 30% reduction in the data delivered, so bandwidth efficiency increased by 30% in this test that was done by our partners. Bitrate mode gave us a 45% decrease in the bandwidth delivered with that same clip. We also computed the MOS scores, which is not shown in this presentation, but what we were able to show is, in the previous presentation, there was a description of what different MOS scores mean. And I think 2 was annoying and 3 was very annoying. So generally 2.4 is a MOS score below which things look very bad. What we're able to show is that with QBR, the occurrences and the rate at which segments fall below 2.4 is almost eliminated, 90% plus eliminated. Obviously, it depends on various characteristics. But the point of it is not just to save bandwidth, but to improve quality even when bandwidth is choppy or inconsistent. This one provides more details on those five tests. You would see that in the first column there is ABR data delivered and the average bit rate. The second set of columns describes what the QBR results were with the quality mode, and on an average you get 30% savings. The third set of columns gives you the advantage with the bitrate savings mode, which gives you a 45% advantage. So we think that QBR is a logical development to ABR delivery. Obviously, it's complementary to encoding developments, codec developments. As I mentioned before, one could encode a video. If you have sufficient time to encode it, you can encode it in perfect VBR. Challenges of streaming in VBR are there, which QBR can solve by the means of a map that I described. It allows compatible client players to make smarter decisions because players get the advantage of knowing what is in the video at any point in time, but more than that, what's coming ahead, so that they can make smarter decisions and get better quality. We are able to see that realistically you can get 30 to 45% savings. Sometimes it can be more, sometimes it's lesser than that, but 30 to 45% is quite realistic without affecting the picture quality, but in many instances, we can stream at a higher bit rate where required. Some of the derivative advantages of QBR is, when we've talked with customers, and by the way, it's deployed in a few different operators and subscription VOD services in the US and in Europe today. Although it doesn't change encoding, we don't claim to change encoding, an indirect benefit is that you can encode better based on what you can do with QBR. So let me explain what it means. Typically, when you're trying to look for an encoding ladder, one would look at what is the best practice. Typically, they might look at what Netflix or Apple would say as a best practice. But it's really depends on where you are in the world, and what kind of network your subscribers are on. If you are on a mobile heavy service, using the same, it really depends on, whether it's 2017 or 2020 or 2014. It's really a function of what kind of infrastructure you're streaming into. So a concern that people have in choosing an encoding ladder is if they choose a very high bit rate as the highest representation, 90% of it is streamed at that level, at least in developed countries. And so because of that, knowing that, people wouldn't really pick a high bit rate as the highest representation because most of it is going to be streamed at that point, and increasing it is basically increasing your CDN costs. With QBR, you're using that high bit rate only when required, not just because you have bandwidth. And also, if you just pick a high bit rate, the concern is that you might be picking a very high bit rate and it will never get streamed. So QBR increases the chances that the high bit rate that you encode in will get streamed. So it has indirect benefits in terms of how you choose to encode, but it doesn't directly change encoding or depend on encoding. So the conclusion is that we have ways to improve streaming quite fundamentally with QBR. QBR metadata provides a useful map of what's coming ahead, which players can use to stream better. We are looking to find efficient ways of collaborating with other companies, and we want to look at standardizing and trying to see if it makes sense, and your input would be welcome, to see if there is a benefit to the industry in standardizing some of the semantics related to QBR metadata. And as you can see from the discussion so far, it's not a replacement to ABR. It's not a different way to compress or a codec. It is compatible with existing ABR schemes, and it is supported by an analyzer between the encoder and the packager, or between the encoder and encryption steps, and an SDK on the player side. Thanks. Yeah, questions?
Thierry Fautier, Kumar, I just want to remind you iOS 11 is VBR encoding. So when you say VBR encoding is a challenge, I want to understand why.
No, I didn't say VBR encoding is a challenge, but streaming in VBR can be a challenge. I'll give you an example why. So let's say you have a video, and it's not nothing to do with a specific encoder or not. But let's say a video is there where there is a complex scene, and that complex scene would typically require a very high bit rate. Let's say for the sake of an example, let's say that you require, let's just make it extreme. Let's say you need 50 Mbps for a specific scene. Would a publisher encode in pure VBR? You wouldn't, right? Because 50 Mbps would be a very high number. It may not get streamed. But QBR doesn't make VBR happen, or we don't claim to say that we can encode in VBR, or VBR encoding is not possible. Sure, you can encode at that high bit rate in that complex scene, but QBR increases the chances that you might actually be able to stream at 50 Mbps, which is the benefit that we provide.
But I don't understand. If I need 15 megabits, it means I need to send it. If the network is not there, then the player will pick a lower bit rate.
That's right. But with QBR, it might actually pick the 50 Mbps. That's precisely what the benefit of QBR is. So let's say that you have, just as an example, let's say that you have a few minutes of simple scene and then a complicated scene. In the race car, you have a variety of different scenes, right? So typically, you have a variation in the complexity of scenes. So when the scene isn't complicated, if the player were to know that there is a complex scene coming up in a few minutes or a few seconds, and that scene requires a very high bit rate, and it is being encoded in VBR, QBR increases the chances that you might be able to stream in that high bit rate. So what you described is, yes, if you encode in VBR, and if the player doesn't have bandwidth, it won't stream. With QBR, it might actually stream in that high bit rate, in that complex scene.
So
it adapts, the player gets a roadmap of what's coming ahead, which can be taken advantage of by the SDK, so that you pick lower bit rates in advance, create a buffer, and use that buffer to pick a higher bit rate when required.
Okay, so you are doing predictive analysis on what's coming next.
In the case of VOD, it's trivial, but yes.
You do that for live also?
We can do it for live. If there's a delay, you can't do it for live if there's no delay.
Okay, thank you.
Unless there is well, with sports it's not possible, but linear programming it's possible, because you can see what's coming ahead in many cases.
So you guys are talking about not changing the encoder, and I admire the fact that you guys are staying in existing technologies and not breaking players with new technologies. But the only thing I could think of your entire presentation was adaptive segment lengths, because you're obviously changing, let's say we're doing 2-second segment lengths at times where it could still be talking head versus a panning camera. Have you guys been looking at those possibilities? And I would even extend that to adaptive GOP sizes, which I know does get into the encoding, but those would be two huge places where you could.
Yeah. So again, it's you could do that, but what we are hoping to enable is better streaming, right? Because you can if I take a video encoded in exactly the same way and stream to two different machines, one being on a great, with a good network, and the second on a mobile or a Wi-Fi here, which is, was trying to do something in, Wi-Fi over here, and I couldn't download it. I'm trying playing a video here, it won't work, right? So two different instances with the same video, it will play differently. So yes, encode side, server side optimization has its place. What this allows is streaming optimization. So it takes the same encoded assets, but streams better based on the specific instances, specific network characteristics.